Lecture 8.2, Part 1, Acid-Base Reactions. Acid-base reactions are double replacement reactions between an acid and a base. A common product in all acid-base reactions is a salt. However, water and carbon dioxide are sometimes also produced. An acid-base reaction is also termed a neutralization reaction. The most recognized neutralization reaction is the one that produces water and a salt, not necessarily NaCl as in table salt. This reaction is typified by a monoprotic acid, which produces an H+, and an alkali metal hydroxide, which supplies OH-. The net ionic equation for this reaction is H+ plus OH- yields H2O. The spectator ions are not important in the net reaction. The heat of neutralization, that is, the heat generated by this reaction, is always negative 56.2 kilojoules per mole and is independent of the spectator ions. A second type of neutralization reaction occurs when an acid reacts with a carbonate or a bicarbonate. The products of this reaction are salt, water, and carbon dioxide. A third type occurs when an acid reacts with either ammonia or an amine. This third type of reaction only produces an ammonium salt without any water. Here are the 7 strong acids and their dissociation reactions. The 7 strong acids are hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, nitric acid, HNO3, chloric acid, HClO3, perchloric acid, HClO4, and sulfuric acid, H2SO4. Sulfuric acid is a diprotic acid. The first hydrogen ion released is 100% dissociated, making the first hydrogen ion the strong acid. The second hydrogen is only partially dissociated and is considered a weak acid. The 8 strong bases come in 2 groups. The first group are the hydroxides of the group 1 metals. These are lithium hydroxide, LiOH, sodium hydroxide, NaOH, potassium hydroxide, KOH, rubidium hydroxide, RbOH, and cesium hydroxide, CsOH. The second group are the hydroxides of some of the group 2 metals. These are calcium hydroxide, CaOH2, strontium hydroxide, SrOH2, and barium hydroxide, BaOH2. Acid properties. Acids have a sour taste. For example, vinegar owes its taste to the presence of acetic acid. Acids cause color changes in plant dyes. For example, the juice of red cabbage changes colors depending upon the presence of acid or base. Acids react with certain metals to produce hydrogen gas. For example, magnesium reacts with hydrochloric acid to produce magnesium chloride and hydrogen gas. Acids react with carbonates and bicarbonates, also known as hydrogen carbonates, to produce carbon dioxide gas. For example, calcium carbonate reacts with hydrochloric acid to produce calcium chloride water, and carbon dioxide. Since acids dissociate into ions, acids are also electrolytes and can conduct electricity. Base properties. Bases have a bitter taste. Bases feel slippery. For example, some soaps contain bases. Since bases cause the production of ions in solution, they are also electrolytes and can conduct electricity. Arrhenius definitions of acids and bases. An Arrhenius acid produces H+, or more specifically, hydronium ions, H3O+, in water. The hydrogen ion binds to a lone pair of electrons on the oxygen in water to create the hydronium ion. For example, hydrochloric acid reacts with a water molecule in an aqueous solution to produce the hydronium ion and a chloride ion. An Arrhenius base produces hydroxide in water. Any metal hydroxide, such as lithium hydroxide, LiOH, dissociates in water to produce the metal ion and a hydroxide ion. Ammonia and amines also act as bases, but these produce their hydroxide ion by removing a hydrogen ion, H+, from a water molecule. The result of these reactions is hydroxide, OH-, and an ammonium cation, such as NH4+. This is a picture of the hydronium ion. The hydronium ion is also known as a hydrated proton because the hydrogen ion, H+, is simply a free proton. Bronsted definitions for acids and bases. A Bronsted acid is a proton donor. That is, it gives up H+ to another chemical species. A Bronsted base is a proton acceptor. It is the chemical species that accepts the H+ from the Bronsted acid. In the picture, the ammonium molecule accepts a proton from the water molecule. This makes ammonia the Bronsted base and water the Bronsted acid. The products are the ammonium ion and hydroxide. The ammonium ion is the conjugate acid of ammonia, which is a Bronsted base. The hydroxide is the conjugate base of water, which is a Bronsted acid. In the Bronsted definitions, there is always a conjugate pair. The difference between the two species, the acid and the base, is a proton. The acid always has one proton, H+, more than the base. In this picture, NH3 is the base and NH4 plus is its conjugate acid. Note that NH4 plus has an H plus more than NH3. A Bronsted acid must contain at least one ionizable proton. Ionizable protons are attached to the halogens, HF, HCl, etc., polyatomic anions, HNO3, H3PO4, H2PO4-, etc., and organic acids, RCOOH, such as CH3COOH. The R in an organic acid is the rest of the organic molecule, with the COOH designating the acid function. Monoprotic acids can only release one proton. Examples include hydrochloric acid, HCl, nitric acid, HNO3, and acetic acid, HC2H3O2. Diprotic acids, such as sulfuric acid, can release two protons. Triprotic acids, such as phosphoric acid, can release three protons. A Bronsted base must contain at least one lone pair of electrons to accept a proton. Lone pairs are often present in anions, ammonia, and amines, which are organic molecules with a nitrogen, such as methylamine, CH3NH2, or ethylamine, CH3CH2NH2. Identify each of the following species as a Bronsted acid, base, or both. Hydroiodic acid, HI, has an ionizable proton. Therefore, HI is a Bronsted acid. It is not an anion, ammonia, or an amine, hence it cannot be a Bronsted base. Acetate, CH3COO-, has no ionizable protons. The hydrogens in the acetate are covalently bound to the carbon. Therefore, acetate cannot be a Bronsted acid. Since acetate is an anion, it can accept a proton to become acetic acid. Thus, acetate is a Bronsted base. Dihydrogen phosphate has two ionizable protons. Hence, dihydrogen phosphate is a Bronsted acid. Since dihydrogen phosphate is also an anion, it can accept a proton to become phosphoric acid. Thus, dihydrogen phosphate is also a Bronsted base.